Hello. I think this is on, so welcome to the MTL seminar. And today we have the pleasure of having one of our own, Vivienne Sze, giving the talk. So Vivienne is an associate professor of EE at this point, at EECS, at MIT. And she's also the director of the Energy Efficient Multimedia Systems Research Group at RLE. She works on computing systems that enable energy-efficient machine learning, computer vision, and video compression and processing for a wide range of applications, including autonomous navigation, digital health, and the Internet of Things. She is widely recognized for her leading work in these areas and has received many awards, which I will not read for you because there really are many. So congratulate her, and let's get to the talk. Thank you very much for coming, Vivienne.
All right, thank you very much, Vicky, for the introduction. So I'm happy to be here for the first seminar of this semester, and I'm really happy to share some of our research at the intersection of computing, energy-efficient computing, and the applications of AI and robotics. I should first mention that a lot of this work is done in collaborations with many students as well as many other faculty here at MIT, so they're all listed below. And then versions of this talk have been done before, so you can actually access the slides on our website. So we know that there's a lot of exciting opportunities in AI and robotics, and right now a lot of the computing for these type of applications are happening in the cloud. But there's many compelling reasons why we want to move the computing from the cloud to the edge and into the device where we collect the data on which we compute. So the first reason for moving processing to the edge is if we want this type of technology to be accessible to people around the world. In particular, if we want the computation or this application to be not reliant on a strong communication infrastructure. And this is really important, as I mentioned, if we want it to be accessible. Another reason for moving the compute to the device where we collect the data is privacy and security. So for a lot of applications like in the finance field or in the we're dealing with healthcare data, the data that you collect, there's a lot of sensitivities related to that, and you might not actually want to send it to the cloud. So it might be better to bring the compute from the cloud to the device itself where the data is actually being collected. And then the last application, or the last reason, is we think about interactive applications, where we need to interact with the environment, and their latency is very critical. So this is robotics or things like AR, VR. You can imagine if you're in a vehicle or self-driving car going down the highway, if you see an obstacle, you might not have enough time to send the data to the cloud, wait for it to be processed, and wait for it to be streamed back. So again, you want to bring the computing into the robot itself, or into the device itself. The main challenge for doing this has to do with the compute cost. So if we take a look at the self-driving cars as the same example, it's been reported in the past that a self-driving car collects 6 gigabytes of data every 30 seconds, and just to crunch or process on this data that's being collected takes over 2,000 watts of power. Right? And this generates a lot of heat, and in fact can take up a lot of space, can take up the whole trunk of a vehicle, and needs a lot of water cooling. And so as a result, we need to find a better solution, and we'll be talking about what these solutions can be. You can imagine that, furthermore, if you shrink down the size of the particular device to something that fits in the palm of your hand, so for example, a smaller robot, or maybe, for example, your cell phone, this is going to be even more significant challenge. Here on these handheld or portable devices, the amount of energy you have is limited by the size, weight, and cost of the battery on these devices. And then also, if you think about existing embedded processors that are targeted for AI and robotics, even those consume over 10 watts, which is an order of magnitude higher than what the typical power budget is for these handheld devices. Typically, for these portable devices, because of the heat dissipation, you're really limited to under a watt of power consumption. Now, if we think about how we address this type of challenge in the past, we could wait for Moore's law and Dennard scaling to give us faster, smaller, and more efficient transistors. But we know that this trend has been slowing down over the past decade or so we really need to have a better solution in order to deliver the efficiency for both energy and speed that we require. And one solution towards that is building specialized hardware. And this can be really thought of how do we kind of really design the computing hardware from the ground up to address these challenges, but also these exciting applications. So in fact, in addition to this, we just have to think about how do we enable efficient computing across the entire design stack. Beginning with thinking about new algorithms. So in the past, we focused on, when we're designing these algorithms for AI and robotics, we're really trying to push on improvement in things like accuracy and quality of result. I think those are really important, but additional things that we need to consider now are things like how do we make them also efficient? So jointly optimizing for things like accuracy and energy consumption, for instance. As we mentioned, we need to think about redesigning the hardware themselves, and this could involve things like new computer architectures where we think about, what are some specialized memory hierarchies that we can use that allow us to efficiently reduce power consumption, and then how can we realize these architectures in actual, circuits and chips. And then finally, we want to integrate this compute into a larger system. So for example, in robotics, we want to integrate it into the robot itself. And so the ultimate goal is to kind of think of the energy consumption of the overall system. And so we need to think about the interplay between compute, sensing, and actuation. So if we're going to tackle energy efficiency, the first thing that we should think about is where does the energy or the power actually go? And so if we take a look at the power consumption, as it turns out, the power consumption is dominated by data movement. So this is some results that Mark Horowitz showed at ISSCC back in 2014. And what we can see here is the energy that's being consumed by computation like multiplication and addition at various levels of precision, from 32-bit float down to 8-bit integer. And we can see, of course, that multiplies consume more than adders, and as we reduce the precision, the energy goes down. However, if you take a look at the cost to read the data that you would need to put as inputs to the multiplier or to the adder, a 32-bit read from a very small on-chip SRAM, 8 KB SRAM, is already going to consume more energy than the compute itself, right, than a 32-bit floating multiplier, let alone as we reduce the precision. And then if we need to go off-chip to, let's say, DRAM to access that data, we're talking about orders of magnitude increase in energy consumption. Just to highlight here on the x-axis here, we're talking about a log scale. So we can see that memory access is orders of magnitude higher energy than the compute itself. So it takes more energy to move the inputs to the compute engine and to move out the results than to perform the computation itself. And that's really where we should focus our attention if we really want to address energy consumption in computing. The challenge here, of course, if we start looking at the applications that we're interested in, is that they use a lot of data. And for example, if we look at autonomous navigation, there's two types of data that we kind of use to understand the environment. So first is semantic understanding. So this is the idea here is that I've given an image of its surroundings. Can we actually, for example, label each pixel in the image to say, this pixel belongs to the ground or the grass, this belongs to the person, this belongs to the sky, this belongs to the dome, so on. So we want to really be able to do this to understand our environment. Typically, we have to process these frames or images at a fairly high rate, primarily if you're traveling at a fast rate and your environment's changing. You might want to actually do this at large resolutions, because this will allow you to be able to see objects that are far away. And then also, so for example, if you look at like high definition, we're talking about 2 million pixels per frame. And then if you want to be able to detect object at different scales, for example, often you have to do things like expand the data and build image pyramids. And this is going to increase the amount of data that you need to process by 1 to 2 orders of magnitude. So this is understanding your environment. You can imagine in navigation you also want to build a map. This is understanding the geometry of your environment, so how far away the different objects are. And you can imagine here, so this is like kind of a stream that's going into the vehicle, and this is the map that it's building. You can imagine that as you navigate for longer, the size of the map is actually going to grow. All right, so we know that in autonomous navigation already, these are some examples of where we use a lot of data. Another thing I just want to emphasize is like understanding the environment. There's various ways of doing this. As we mentioned, there's depth estimation from an RGB estimating the distance of the pixel. We talked about semantic understanding. The way in which you can actually understand your environment depends on what technique you apply. And as of today, typically the state-of-the-art approaches which give the highest accuracy rely on deep neural networks. The challenge with deep neural networks is themselves they have hundreds of millions of operations as well as weights that are required to perform the computation. Okay, and when we compare it to an application that we all widely use, for example, video compression, which is happening on all of your phones when you're watching video or doing Skype or FaceTime with a friend, we're talking about orders of magnitude, so at least 100x, if not more, increase in complexity per pixel compared to video compression. So if we really want to make technologies such as DNNs accessible and as widely used as something as video compression, we really need to close this gap on computational complexity. I should also mention that obviously DNNs are used beyond just autonomous navigation, but on a wide range of AI-driven applications, ranging from things like computer vision to speech recognition. So if you're saying, OK Google, or talking to Siri, you're using DNNs. It's also been shown to be really effective in things like gameplay. So it's been shown that, for example, deep neural nets has overcome this grand AI challenge of playing Go, and back in 2016 already beat the world champion in the game of Go. And the reason why Go was thought to be a grand AI challenge is that for every given position or every given time, the number of positions exceed the number of atoms in the universe. And also in medical applications. So we're seeing a lot of exciting applications there. So how can we make neural networks or make the processing of neural networks more efficient? That's the first question we want to answer. And so as it turns out, there's actually many properties of deep neural nets that are friendly towards efficient computing. So the first thing is, actually, if you break it all the way down, if you look at per layer in the neural net, it's only just doing a bunch of multiplies and accumulates. So high parallelism is actually possible. So you can achieve high throughput, you can have high speed. The main challenge, which should be no surprise, is actually the memory access, which is the bottleneck. So if you're performing a multiply and accumulate, which we call a MAC, for each MAC that you perform, you need to have 4 memory accesses. You're going to have 3 reads, the filter weight, image pixel, and partial sum, and then you're going to have 1 write, which is the updated partial sum. So it's already a 4-to-1 ratio. In the absolute worst case, and you would not want to do this, is that if you have to read this data and write this data to DRAM, off-chip memory, and we're talking about a 200x increase in terms of energy per memory access as compared to the energy for the computation itself. And just as an example, if you think of something like AlexNet, which has 700 million MACs, you're talking about 3 billion DRAM accesses to drive this. And of course, with even more modern CNNs, this would be consistently the same challenge. Again, there are some properties of a DNN that we can exploit to reduce this memory access bottleneck. In particular, there's what we call input data reuse opportunities, which means that if I read some inputs, I can use them multiple times for multiple computations. So for example, in convolutional neural nets that are widely used for processing image data, we have what we call convolutional reuse. And that means that the activations in the pixels, or actually activations of the weights that are being used, are going to be reused multiple times for multiple operations as we kind of slide or convolve the filter across the input feature map. Another example is what we call feature map reuse. And so that means that each activation in the feature map, or you can think of this as each pixel in your image, is going to be reused multiple times across the different filters that are applied to this input feature map. Again, this is a type of processing that occurs regularly in deep neural nets. Another thing that happens in deep neural nets is often for a given filter, you might apply it to multiple input images or multiple input feature maps. And what that means is that each weight in the filter is going to be reused multiple times across the different inputs. Okay, so there's a lot of different input data reuse opportunities. And the way that we can exploit this is by designing custom memory hierarchies that allow us to exploit the reuse at low-cost memories. In particular, what we mean by low-cost memories are memories that are basically located very close by to our compute unit. So shown here is a multiply and accumulate, and we have a register file here that's right beside the MAC itself. And also that this memory is small. So typically, for example, under 1 KB of memory, so that way your bit lines and word lines are of low capacity, so you don't have a lot of switching energy there. When we combine these register files together with a MAC and its own control, we typically call this a processing element. And then we could imagine an architecture that has an array of these processing elements. We might have a slightly larger global buffer that they all share. And then in the worst case, they go to DRAM. And just to give you an idea in terms of what the energy costs are associated to these different levels of the memory hierarchy, let's say you do a multiply and accumulate, that's 1x. Reading from that small register file that is nearby, which is under a kilobyte, would also be 1x. Reading from your neighboring processing element would be maybe 2x. Reading from that larger memory, which is about between 100 and 500 bytes, would be 6x the energy. And then, of course, as we mentioned, going off chip to DRAM would be the worst. In general, farther and larger memories consume more power. So the key idea here is that ideally, you'd like to read as much as possible and exploit as much reuse from this register file. The challenge, of course, is we just said that these neural networks are very large, and this register file is very small. So the question is, how do we take this very large neural network, chop it up into smaller components, and what is the order that we should process those different components? A typical analogy I think might be useful here is that you can think of this register file as like your own backpack. If you had a lot of work to do, what is the work that you should put into your bag, at the beginning of the day so that you can do the most possible work without having to go back to your dorm room or your home and so on, right? So every single time you have to go back, that's going to be a lot more effort, but you can't store that much in your bag. So that's basically the idea that we're trying to deal with. And so there's been actually a lot of research in this space in terms of how do we basically chop up the data and what is the order to process, and typically we refer to this as the data flow. So there's a couple of examples of this. So the first approach is what we call weight stationary, and the idea here is that you want to store the weights of the neural network into this small local memory. And as a result, the weight energy is minimized. But of course, your activations and partial sums, the other data types still have to move through the system, for example, through the on-chip network and from the global buffer. Two examples of work that does this that's quite well known is the TPU from Google, as well as NVDLA from NVIDIA. Another strategy that people take, well, they're saying, well, weights, we just read it once. But if we think about the partial sum, you need to read and write it. So that's two memory accesses. So wouldn't it be better to store that in that local memory? So that's what we call output stationary. So effectively, the partial sum or the accumulation of the partial sums, which become the output value, is stationary within the processing element. And then, of course, the trade-off is that the weights and the activations have to flow through the on-chip network and the global buffer. And examples of work that do this are some work from KU Leuven, as well as some work from the Chinese Academy of Science, thinker work. A third approach could be you can just think of, well, there's three data types. So the third data type is input stationary, where the input is stored in the local memory. And this was explored also in a research paper from NVIDIA SCNN. Another approach, which is something that we developed within our own group, is saying, well, rather than focusing on one particular data type, can we actually try and reduce the data movement collectively of all three data types? And one approach we came up with was what we call the row stationary data flow. And the idea here is that within each processing element, rather than exclusively storing weights or input activations or partial sums, we basically process one row of weights with respect to input activations. And so this allows us to maximize the convolutional reuse within the register file for the filter row and the feature map, input feature map, and then also the accumulation for the partial sums for that 1D convolution. So this is just one dimension, but of course we want to extend it to more dimensions than that for CNN. So for example, you can stack multiple of these processing elements together so that they can end up performing, let's say, a 2D convolution as shown here. You can also see a couple of important features here, which is that, for example, the accumulation across the different rows of processing elements for the partial sums are all happening within an array so that they don't actually access the global buffer, which is more expensive. You'll also notice that horizontally, the row information for the filter shown here in green is repeated. That means I read once from that global buffer, and then I can share it spatially across multiple processing elements. And similarly, diagonally, in blue is shown the reuse or spatial reuse that you can achieve for the input activations. If you want to go into more details, I would recommend that you take a look at the ISCA paper, but the overarching message of this is that what we're focusing on here is trying to optimize for the overall energy efficiency as opposed to the energy efficiency of a specific data type. Okay? And one outcome of this is an improvement in the overall energy efficiency. So just to give you an example here, so this is the energy consumed per MAC for the various different data flows. You'll notice that in the weight stationary case, the green portion, which is where the weight, the energy cost of moving the weight is minimized, and that's great, that's by design. But then the partial sums and the pixel energy is larger. In 3 variants of the output stationary approach, where we're trying to minimize partial sum, you'll notice the red portion of these graphs are very small. And again, that's by design. But then the weights and the partial and the pixels are higher. We don't have time to talk about no local reuse, but in the row stationary case, you can see that it achieves the best overall energy efficiency, though if you looked at the breakdown, it's not the minimum energy per data type itself. So the high-level message here is it's always good to kind of do a global optimization as opposed to optimizing for a specific data type. Some other things that we can also naturally exploit in a convolutional neural net, or DNN in general, is sparsity. So anything multiplied by a 0 is going to be 0. So you can actually skip the multiplication operation. So if you can recognize that it's a 0, you actually don't have to read the other operand, and you can skip the multiplier and the adder, so you actually have less switching. So you can save, for example, here 45% in power consumption. Another thing that you could also do is if you have a whole bunch of zeros, you can actually apply lightweight compression, for example, run length compression, and then as a result, you can reduce the data movement. So this is showing here if we applied this for things like the activation on the data traffic for the DRAM would be reduced almost by 2x. So one way to demonstrate what this was, we realized both the row stationary data flow and this exploitation of sparsity in this IRIS DNN accelerator that we published at ISSCC in 2016. As you can see here, it has 168 processing elements, so 14 by 12. It has a shared global buffer of 100K bytes. It does some compression, as we talked about, and has before it talks to an off-chip DRAM. It was basically implemented in 65 nanometer CMOS. And here's a die photo of it. Now, because of a lot of the reuse that we exploit by reading primarily from a local register file or by sharing with the neighbors, we're actually able to reduce the amounts of memory access from the shared global buffer by 100x, and the amount of off-chip memory accesses by over 1,000x. And so as a result, you can achieve an order of magnitude reduction in energy consumption compared to mobile GPU at the time. We were comparing to NVIDIA's TK1, which was in 28 nanometers, and this is for AlexNet. So for more information about this, you can visit the IRIS website, and this is, of course, in collaboration with Joel Emmer. Okay, so if we take a step back, though, let's say you say, I don't care about hardware, I'm a systems person, and I just give me a solution. And what I really care about is the trade-off between energy and accuracy. What are the implications of this, right? So shown here on first the x-axis is the accuracy. This is average precision measured for an object detection task, and this is on a linear scale. And on the vertical axis, we have the energy consumption per pixel measured on an exponential scale. Okay, so first of all, if we look at comparing handcrafted features, for example, Hog or histogram-oriented gradients, which was considered state-of-the-art before this whole resurgence of neural nets in 2012, we can see that when we compare Hog to something like AlexNet, which is a neural network, or VGG, that AlexNet and VGG give double, if not almost triple, improvements in accuracy. And this is why folks are super excited about DNNs, right? But if we look from the energy point of view, and in particular, I want to mention that these values are all measured energy points. So these are 2 chips that were developed within our group to do basically Hog-based object detection. And then this is the IRIS chip that we just talked about. I should just mention that these students started their PhD at the same time, completed their PhD at the same time, taped out at the same time. So almost a controlled experiment if you want to think about how much optimizations. They're both in my group. They both graduated now. We've taken measurements from these particular platforms and compared how the energy consumed with specialized hardware between handcrafted features and DNN features. And what do we notice? I just also want to give you a benchmark here. Video compression is typically around 1 nanojoule per pixel. What we show here is that, first of all, interestingly enough, with Hog-based features, the energy required to understand video using Hog features is actually going to be cheaper than compressing the video. So using hog-based features, in theory, you could be as ubiquitous as video compression. However, when you start looking at things like AlexNet and VGG, the energy consumption increases substantially in terms of orders of magnitude. So like 300x and 10,000x. So one thing to think about would be if I were to ask the audience here, if I told you on your cell phone, I will double the accuracy, but your cell phone battery is going to die 300 times faster, who here is interested in that technology? Right? What if I tripled the accuracy and your cell phone battery dies 10,000 times? Right? I think so. What I'm trying to show here is that energy consumption is really critical, just as accuracy is. Right? So really, we need to consider the implications between both of them. We're going to optimize both. And what we actually want to try and do is reduce the energy consumption and ideally maintain the accuracy or even improve it. Okay? And so we've shown here that you can try, and these are already with like specialized hardware, but we still need to look at other ways we can further reduce the energy consumption. And so again, there's been a wide amount of research in the space of looking at, can we change the algorithms in conjunction with the hardware, looking at kind of the co-design of algorithm hardware in order to enable efficient processing of DNNs. So in fact, our group has spent quite a bit of time kind of surveying the field and actually generating various tutorials and survey papers on this particular topic. So I would invite you to take a look at these two, both the slides as well as the survey paper. Actually, Joel and myself are in the process of writing a book, which should be available within the month. We also teach a class here at MIT on this, if you're interested. But through this process, what we did, we actually identified various limitations on the existing approaches, right? So the first thing is let's look at the DNN algorithms briefly. So there's several you can kind of categorize the popular ways of making the DNN algorithms more efficient. You have things like network pruning, where you're trying to make the weights sparse. You also have compact network architectures, where you're trying to decompose these large filters into smaller filters, and then also reducing the precision. For example, rather than using 32-bit float, can you use 8-bit or even 1-bit and so on? A lot of this work focuses on reducing the number of multiply and accumulates, the number of max and the number of weights. The question that we want to ask is, does this actually translate into energy savings and reduced latency? Right? Because that's the ultimate goal from a systems perspective that we care about. So again, we just saw the slides a few minutes ago, just a reminder that the data movement is what's really driving the energy consumption. And as you can imagine, if you're thinking about things like weights, the energy of the weight really depends on where the data actually comes from, so the memory hierarchy and the data flow. So did I read the weight from the register file, or did I read the weight from the DRAM? That's going to have a big implication in terms of the cost of the weight itself. And so in other words, all weights are not created equal. So you can't just count the number of weights and say, oh, this is going to be more energy efficient. It really matters in terms of what the underlying hardware, and what are the properties in terms of the weights reuse, for example. So one effort in terms of better understanding where the energy goes is, in our group, we tried to build this energy evaluation tool that allows you to basically put in the shape of a DNN, so basically the dimensions of a DNN filter and the activations, as well as the sparsity of the DNN's weights and input data. And then based on this, it would actually try and figure out a breakdown in terms of the energy consumed for the different levels of the memory hierarchy and the energy cost for the compute. And then you can end up seeing the energy cost per layer, right? And what is the key observation for using this? One is that the number of weights alone is not a good metric for energy. And this should be no surprise, because we actually talk about moving a lot of different types of data around, right? And so all data types should be considered. If you look at GoogleNet, right, the weights only account for 22% of the energy cost. The output feature maps and input feature maps also consume a lot of energy as well, okay? So then the question goes, now that we know that number of weights is not directly aligned with the energy consumption, how can we actually take energy into account when we're designing the various DNNs? So one way you can do it is applying it to that technique of pruning that we talked about to make the weights more sparse. So in the past, the one way you could do this is that you would actually remove weights that are small. So we prune them based on their magnitude. And this is shown to be quite effective, right? So this is showing the energy consumption of AlexNet. This is for the same accuracy. You can actually remove enough weights so that you can actually half the energy of the neural network without sacrificing much accuracy. However, the question goes, well, does the magnitude of the weight have any implication in terms of energy? Or could we also, try and remove the weights that consume the most energy instead? And so one way that it could do that is you could sort the layers based on the energy consumption and then prune the layers that consume the most energy first. And that's in the hopes of saying that basically the weights that I remove will consume more energy, right? And what we were able to show there is that for the same accuracy, you can now reduce the overall energy consumption by 3.7x, right? And so really the high-level message here is that if we're trying to design for reducing energy, then we should really directly incorporate energy into design of the algorithm as opposed to using proxies like number of weights, right? Another important metric that we care about is latency. In particular, basically means like how fast, how much time does it take before when I get the image to when I have the result. And this is some work that was posted by Google's mobile vision team. And what they really want to show here is that the number of operations doesn't necessarily approximate latency well. So shown here on the x-axis is the number of operations, or number of max in the millions. And then vertically here is the latency. And what they are able to show here is that for a given number of max, you can have a 2x swing in terms of the latency. And then for a given latency, you can have a 3x swing in terms of the max, okay? So as a result, you can't directly say based on the number of max, this is how fast it's going to run. So in collaboration with this Google mobile vision team, we looked at, can we apply the techniques that we looked at for energy-aware pruning in the same fashion as basically incorporating it to support latency. And together we developed a thing called NetAdapt, which is a platform-aware DNN design tool. The idea is that you want to automatically adapt a pre-trained DNN network for any given mobile platform. And now if you're Google, you need to be able to support a wide range of mobile platforms, and you might not have the ability to do energy modeling or latency modeling for all of them. So what we actually want to do is take empirical measurements for a given platform and then automatically adapt for that. So you don't need to know anything about its underlying structure. So the algorithm works as follows. You take a pre-trained network in, and then for NetAdapt, you actually also take in a budget in terms of this is your latency budget, energy budget, or a combination of that. NetAdapt will generate a bunch of network proposals, so some modification to the network itself. We are going to measure the speed of these various different proposals on the platform itself. And then these empirical measurements are going to be sent back to NetAdapt, which will inform it on how to generate the next set of proposals. And this is an iterative process. I don't have too much time to go into the details, but again, the code is all available on the NetAdapt website, so we welcome you to come visit it. But what are the implications of doing this? The implication of doing this is that you get a much better trade-off between accuracy and latency. So shown here on the x-axis is latency itself, and on the y-axis is accuracy, and you can imagine upper left is going to be better. And what we're showing here is NetAdapt is, the various iterations of NetAdapt generate these red dots, or these like kind of a trade-off in terms of latency and accuracy. And then you can see that compared to handcrafted based approaches, for example, the sizing of MobileNet, you can actually achieve about a 1.7x increase in speed without any loss in terms of accuracy. I should also mention that this work was done on a very small MobileNet. You can now imagine that it's easy to take a large neural net like AlexNet and make it more efficient, but it's going to be a much more difficult task if the network itself is already quite small and you want to further improve its efficiency. So we really targeted kind of the smallest MobileNet that we had here in order to show that we can achieve this improvement in trade-off. This also can be thought of as a form of neural architecture search or network architecture search, which is now gaining a lot of popularity. Okay, so this is for an image classification task. We also want to show that it actually works in other tasks as well. So for example, on FastStep, this is a depth estimation approach where I given an RGB image, rather than taking an image and giving it a single label, in depth estimation, you basically label each of the pixels, right, in terms of their depth. So you can imagine it's a combination of reduction or encoder partial part of the network, which is similar to classification, but then you need to expand it as well so that you're getting depth estimations for every single pixel. This work is in collaboration with Surtesh Karaman, who's in the Aero Astro department here at MIT. And so again, we want to show, basically ask the question, does NetAdapt and all these other tools work for these types of networks? And indeed it does. We're able to show that by applying NetAdapt and compact network architecture design and depth-wise decomposition, we can achieve high frame rates for depth estimation on an embedded platform, particularly TX2 here. So just to walk you guys through this again, on the x-axis, it's the frames per second for an embedded GPU, which is Jetson's TX2. On the y-axis is the accuracy measured in delta 1, which is the percentage of pixels which are within 25% of the correct depth. And so you can imagine upper to the right is better here. And so the fast depth is shown here in the red star, and so you get an order of magnitude speed up at comparable accuracy. The other thing is, so we presented this at ICRA, which is a robotics conference last summer, and we also want to show that it could work live, so we actually captured some real-time footage there and ran it on an iPhone. On an iPhone, it can run at 40 frames per second. And again, all the code for fast depth is available online. So that's the algorithm side of things. So the main takeaway for in co-design with algorithms is that it's important to incorporate real hardware metrics like latency and energy into the design of the algorithms. On the hardware side of things, it's also pretty interesting. So we have all these exciting ways of making the network more efficient with pruning, compact network architectures, reduced precision. But then now the challenge for the hardware designer is that there's no guarantee as to which technique the algorithm designer is going to use, or if they're going to use any of these techniques at all. Right? So as a result, you have a very diverse set of workloads that you now need to support, and ideally support them efficiently. So you need much more flexible hardware moving forward to do this. And so some of the challenges with doing this is if we take a look at existing DNN architecture design, right? So specialized DNN hardware often rely on certain properties of the DNN to achieve high efficiency. So a typical architecture that you'll see is that they have an array of multiply and accumulate units. And what they'll do is they'll read a weight from the memory and then reuse it multiple times across the array, or read an activation, reuse it multiple times across the array. And this is, of course, because, as we mentioned, data access and data movement is expensive. This is fine, but then the issue here is if you take a deeper look, the amount of reuse that you can get across the array and the array utilization itself depends on the number of channels, the size of the feature map, and the batch size of the algorithm itself. And these are two different variants of doing that. You can just see the reuse dimension depends on properties of the DNN. And this becomes very challenging when you consider all the different types of network architectures of DNN models that are out there now. In particular, as we mentioned, there's this trend of decomposing these very large filters into smaller filters. We call them kind of compact or efficient DNNs. And as a result, for each of their dimensions, it's becoming much smaller, and as a result, there's less reuse opportunity. So for example, if we think of a depth-wise layer, which is widely used in mobile nets, it only has one input channel. Right? So as a result, if you're looking for reuse on the input channel dimension, you can see that it's going to be very narrow in terms of, you might have a whole array of max, but you have very limited reuse. This is also going to be a problem as we scale up the architecture. Ideally, as you add more resources, you'd like to build more cores, more PEs, you'd like your system to go faster, but if the reuse is very limited to only one part, your utilization of your array is going to go down. And of course, if you have sparsity, it's going to be very difficult to exploit sparsity. So there's a couple ways that you can combat this. One is that you need a more flexible data flow. So for example, if we use a spatial accumulation array, which is kind of like weight stationary, or temporal accumulation array, which is like output stationary, the amount of utilization of your cores is going to reduce. But if you have something like row station, which allows for more replication, you can actually fully utilize your array. Another important thing is actually the delivery of the data, which is very critical. So this is typically the on-chip network that we're talking about. So how do I deliver data from, let's say, the global buffer to the rest of the processing elements? And you can have an array of different on-chip network techniques. On the one hand, on the very right-hand side here, you can have network architectures that are low bandwidth but high spatial reuse. And this is going to be really useful for those very large neural nets that people had looked at before, which has a lot of reuse. And what that basically means is that in the global buffer, I only need to read very few amount of data, and then I can broadcast it across all of the Ps. So that's very similar to what we're doing now. So let's say I'm the global buffer, I'm broadcasting information. You guys all get the same information, no matter how many processing elements there are. And that's great because we can reuse that data a lot. However, if you look at, again, more modern CNNs, which tend to be more compact, the amount of reuse is much less. So you want to basically have networks or on-chip networks that are on the other extreme on the left-hand side, where instead of broadcasting, we want unicast so that each of the processing elements, if you guys are processing elements, would get unique data to process on. Right? So now I'm going to have high bandwidth from the shared global buffer, and then low spatial reuse, because we're not reusing data across the different processing elements. So if we really want to support a wide range of DNNs, we actually have to support this whole range of on-chip networks. And one solution for this is going to be an all-to-all network that would satisfy all these conditions, but it's going to be very expensive and not very scalable. So an alternative which we developed within our group was looking at hierarchical mesh, which is breaking down the on-chip network into 2 tiers. At the very lowest level, you have clusters of these all-to-all connections. And then at the higher level, you use a mesh connection, which is much more scalable. And so by doing this, you can actually support all the different data delivery patterns that you want, both in the high bandwidth case as well as the high reuse case, and then the combinations in between, the various forms of multicast. And at the heart of it, this is what the key idea was in the second version of Iris. This allows us to balance efficiency and flexibility. So as a result, with this hierarchical mesh, we can support a wide range of different filter shapes, both large and compact. And of course, this includes different layers, not just convolutional, but fully connected, depth-wise, and so on. Shown here is basically a plot across these different layers. You can see that the second version of Iris compared to the first version of Iris gives you over an order of magnitude speed up. It also supports both dense and sparse workloads. The key thing here is that, as we mentioned, sparsity is great, but if the overhead to detect, let's say the zeros is very high, if I ended up giving you a dense workload without many zeros, there's going to be a lot of overhead. And so you need to balance that as well. That's also present within the second version of Iris. And then we also have a very scalable architecture. So increase the number of PEs, the throughput also increases. So when we compare this to the first version of Iris, you get an order of magnitude improvement in both speed and energy efficiency. Again, this is work with Joel Emmer. Okay, so that's basically some of our solutions to these problems, but we believe that there's a much wider range of solutions out there. In fact, there's a huge amount of effort in terms of designing deep learning or DNN processors out there. So I think what's really needed is some form of an evaluation tool that will allow us to systematically evaluate and compare all the different types of deep learning processors. And if we can do that, we can also rapidly explore the design space. So towards this effort, we've looked at developing tools to do this, in particular the Accelergy tool, which is a method to get early stage energy estimation at the architecture level. So basically what it involves is if you can define the number of processing elements you have, the size of your, let's say, global buffer, the size of your memory hierarchy, and your on-chip network, it can give you some sense of what the energy consumption is. And by being able to do this at the architecture level, you don't have to go all the way down to RTL, place and route, and even tape out and so on. Another benefit of this is that an area of emerging interest is using new technologies to do processing of DNNs, in particular things like memristors or optics for processing in memory, or with new technology. And so this will also have the flexibility to allow us to do that, where you can plug in new device technologies to get a architectural estimation of the implications of that new technology. This is combined with something called time loop, which Joel Emmer designed in NVIDIA, which allows you to automatically map the workloads to these architectures and gives you kind of the action counts, like how often you read from this and that. And so this tool is all open source. It's called on the Accelergy website. We're also using this for the course that we're teaching. A tool is only good as accurate it actually is. So we also showed that Accelergy, we validated on Iris, and it can achieve about 95% accuracy on Iris based on post-layout simulations and show like a pretty accurate breakdown. Okay, so for the last kind of 10 minutes or so, I want to kind of diverge from, this is all DNNs, great, but there's also a lot of exciting problems beyond DNNs that are out there, particularly even related to robotics. The first thing is visual inertial localization. Right? So the first thing you need to do when you need to do autonomous navigation is figure out where you are and where you're facing. Right? That's the first step, and that's what localization effectively does. It basically takes in a stream of images that are located, let's say, on the robot, and then an IMU, which is the accelerometer and gyroscope, also located on the robot. You can fuse those two things together. through a process called visual inertial odometry, which is, you can think of it as a subset of SLAM if you're familiar with simultaneous localization and mapping. And then the output of this is to generate basically a 3D pose. So basically in the 3D space, if you're talking about, let's say, a flying robot like a drone, where are you in the 3D space and where are you actually looking? So this is a video of like basically a camera mounted on a drone flying around, and using visual inertial odometry, this is an estimation of where it actually is in the 3D space. If you're navigating around an unknown environment, you might also want to generate a map while you're doing this. So that's why you have the localization, the mapping. This is also widely used in applications like AR and VR, because you have the same types of challenges as well. So in fact, the student, Amr, who worked on this for his PhD, is now at Facebook Reality Labs working on that. So we were able to do this all at under 25 milliwatts. We built this chip, or designed this chip called Navion. It's the first chip that performs complete visual inertial odometry entirely on chip. So it does all the processing for the front end of the camera, so feature detection, tracking, and outlier elimination. It also does some pre-integration on the IMU data from the accelerometer and gyroscope. And then it does a full optimization on the back end to fuse the camera information and the IMU information together to get an estimate of the pose itself. The chip was fabricated in 65 nanometer CMOS. It's 4 millimeters by 5 millimeters. You can imagine it's small enough to mount on these drones. When we compare it to mobile and desktop CPUs, we're talking about 2 to 3 orders of magnitude improvement in energy efficiency. I also want to highlight that even though it's under 25 milliwatts, it still runs in real time, so all the way up to 171 frames per second. And then the key idea to make this happen or make it efficient is how we handle the data. That's the overarching theme here. We really integrate all of the processing of the data on chip itself. So again, all off-chip processing and storage is eliminated because we saw that going off-chip is expensive. And so if you're going to move all of that data on chip, it could also make for a very huge chip, which we don't want. So we also have to apply various optimizations on chip to reduce the data cost. So for example, we applied low-cost frame compression to reduce the visual information. And on the back end, when we're doing the pose graph optimization, we exploit sparsity and in both the graph and the linear solver. So we're able to reduce the overall memory on chip to under a megabyte. And this work was done in collaboration with Surtesh Karaman. Once you figure out where you actually are when you're trying to do navigation, you also want to figure out where you want to go. That's usually important as well. And that typically depends on what the task is. So if your task is what we call robot exploration, what's effectively happening is I'm dropping you into a completely unknown environment, and your overall goal is how can I see the most or explore this environment as fast as possible with going to as few places as possible. One way to do that is by computing Shannon's mutual information, which basically is an information theoretic way of telling you what part of the map will have new information compared to what I already know. So you can imagine the first step would be you have various candidate locations that you can go to. So shown here is basically the map that you currently have, where light gray is that places that you know that are open, and then dark black is a wall, and then dark gray is unknown. So you have to be like, oh, where should I go to scan to get new information? The scan could be like with a depth sensor, like a LiDAR. So you can compute the mutual information of this map, basically telling you where should I go to get the most new information. And then you would move there, you would scan it, right? And then you would get an updated map. And so shown here below is a video of an actual miniature race car that's actually, in fact, doing that. The mutual information surface is being computed here, and this is just like its path planning. You can see that it's trying to go to the places where the mutual information surface tells it it's very bright, so it can find out more about the actual map itself. Now, it's very similar to deep neural nets. The computation for mutual information is also very parallelizable. In fact, what it is that you have this depth estimation beam that you're scanning, like you imagine a LiDAR just scanning across. So all of the beams, the information that these beams are gathering, could be all computed in parallel, right? So these could all be multiple cores. The challenge here is that, okay, so once you have all these cores, you would add them all together. The problem is that all of these cores need to access the same memory, which is storing the map, right? And for those of you who design memories, you know that typically, for an efficient SRAM, you're limited by about 2 ports. As you add more, the hardware increases, the energy cost increases. So one of the challenges is that how do I keep all of these cores busy if I'm only limited to 2 cores per 2 cores for the memory itself? So what we can do is we can take a look at more at the access pattern that we have as we're scanning these beams. So shown here in the number is like basically the order at which we're going to access each of these beams. And what we can do is then we can take this map and divide it up into separate memory banks. And then the question is, how should we bank the memories such that we can maximize the utilization of the cores, or in other words, ensure that these cores have minimal conflicts, right? So one way of thinking about this is that for any given color, so here on the right-hand side, we're showing basically how we banked it, and each bank is a different color. For any given color, any given number only appears in that bank twice because we only have a 2-port memory. So for example, in this yellow or bank 6, the number 5 only appears twice, right? So this is one of the banking patterns that will allow us to ensure that the cores can run without too many conflicts. And in fact, Peter, who worked on this, has now developed various proof to show that this is provably optimal. And so by doing this, you can actually compute the entire map, the mutual information of the entire map, in under a second, whereas in the past, mutual information was known to be very expensive, so they could only compute like some subset of points. But now you can actually compute it for the entire map, so you can know like what is the absolute optimal place to go to. And this gives 2 orders of magnitude speed up compared to a CPU at 1/10 of a power. One final thing that we've been looking at is even beyond robotics is looking at the application of efficient computing to the healthcare space. So in particular, looking at neurodegenerative disease disorders. So we know that dementia affects 50 million people worldwide, and this number increasingly grows. One of the big challenges in this space is the evaluation or the assessment of potential patients. They can often be very time-consuming, require to train specialists. You need to go into the clinic to go do this. They might ask you things like, what day is it, what year is it, so on, or you can have to draw a clock. The other challenge for this is that because it's expensive, people often go very infrequently. So they might go maybe once or at most twice a year. Also, it's very qualitative, so different specialists might give you different results, which is unfortunate. So this is a big challenge. And so this is a problem that both myself, Thomas Helt, and Charlie Sodini have been looking at together. And what's been super exciting is that there has been efforts that are clinical studies that have shown that eye movements actually give a quantitative information about the neurodegenerative states of subjects. So technically speaking, you can use eye movements to be a quantitative evaluation to complement the specialist assessment, and it can tell you the progression or regression of a given disease. So for example, if I give you a certain drug, is it working or not working? The challenge is obtaining these eye movements still requires very specialized, expensive equipment. For example, high-speed cameras. You need to constrain the head and have IR illumination. So as a result, the patients still need to go into the clinic to obtain these measurements. And so what we've been working on together is to try and figure out, can we actually replicate these studies but using very low-cost equipment like a smartphone or a tablet, right, and check the eye movement of a particular patient and collect data there. And indeed, we're able to show that we can replicate the performance on high-speed camera with, for example, an iPhone 6. So this is showing a distribution of the reaction time of the eye. And so by being able to do this, that means that a patient can take these devices, do a lot of these measurements at home very frequently, and they'll collect a lot more data and provide it to the clinician to have a better assessment. In particular, if you're interested, we're looking for healthy subjects always for this particular task, because we're trying to have a good baseline for the clinicians to compare to. So if you're interested in participating on this, please feel free to reach out to me. We're very excited to have the community participate here. One last thing is looking at sensing. So we talked that computing alone is not the only thing that consumes power, but also sensing. In particular, we've been looking at time of flight sensing, which is depth estimation. So if I emit a pulse, how long does it take for that pulse to come back? That will tell me the depth of a given environment. This is often very expensive because you have to emit a pulse. Anything that's active can consume a lot of power, so up to 20 watts for 8 meters. And so one of the projects that we've been looking at is, can we co-optimize the computing and the sensings? In particular, can I reduce the on time of the sensor and then fill in the blanks with computing itself? So for example, you often collect depth and image information at the same time. Let's say we turn both on at time 0, but at time 1 and time 2, I only keep the RGB, basically the 2D camera on, and then estimate what the depth would be for the depth, but I don't turn on the depth sensor. Now, the key challenge here is that you want to maintain quality, but also the algorithms that you use to estimate this depth also has to be lightweight, otherwise you cancel out the benefits, right? So we're actually able to develop algorithms that can run on these very lightweight embedded processors at under half a watt. And so this is just qualitatively showing you the impact of this. So this is, let's say, an RGB image. This is the ground truth depth map, where if I collected the depth, time of flight depth map at every single frame, and then if I only enabled that sensor every 9th frame, and then filled in the blanks with an algorithm, so I have a 0.7% loss, but as a result, I reduce the on time by basically 89%. Okay, so in summary, basically the key idea here is we want to enable energy efficient AI so we can extend the reach of AI beyond the cloud. So this enables us to reduce communication requirements, enables privacy, reduces latency. So we can use it in a wide range of applications from robotics to healthcare. But in order to be able to do this, we need to really think about cross-layer design, not just efficient algorithms, but also efficient hardware, in particular specialized hardware. And this will be critical for the progress of AI over the next decade. There's a lot of stuff here, so I invite you to go visit our website to check out the slides, which are available there. But also, there's also various resources. So again, if you want to know about efficient processing for deep neural nets, we have a whole tutorial paper of that, and then the book should be out in a few weeks. We also have a bunch of slides on our tutorial website. Actually, there's a sample of the book on this tutorial website as well. We have an on-site course here at MIT that teaches this, and then also we have videos and tutorials that are available online as well. And then finally, I want to just, of course, acknowledge the students who obviously do all the work, as well as collaborators and various funding agencies. Thank you very much.
All right. Super.
Thanks.
Thank you very much for a super talk. We have no time for questions, so unless somebody's dying to ask something, I think we'll just let Vivienne go and relax. Any questions? You can ask. Oh, no. Super. Thank you very much. It was fantastic.
Thank you. And if you're interested in volunteering again for the eye study, we're very much looking for folks. Thank you.